that is tuning into any of our multiple streams here for Hope 2020. Our next segment will feature Dominic Muren, founder and principal of the Humble Factory, a design lab in Seattle, Washington, which develops tools and technologies that increase the capabilities of makers around the world. More than a decade ago, the democratization of 3D printers and CNC 2D cutters using lasers and routers brought with it a breathless theorizing that mass customization and bespoke production of objects would make global supply chains a thing of the past. This talk will present an alternative technological development path, one where materials are sourced entirely from constituents of living ecologies and the materials they produce. This video does run slightly long. If it does exceed the length of these segments, then we will ensure that the entirety of the video will be available via our YouTube channel.
Hello, everybody. I am so excited to be able to come here virtually to present this to you all. I'm super excited to be speaking at Hope. I've followed this community for so long, and this is my first time talking. And I'm also excited to talk about how we can make a pursuit of truly open source objects and kind of explain what that means. But first, let me get into what open source really means. Outside of software. In open source, we often talk about free as in freedom, which means once you get the thing, you can do anything you want with it. You can modify it, break it, hack it, whatever. So you're free to do those things, but it might cost you money to get. And then we talk about things that are free as in beer. So you might pay for or you might get a piece of software for free, but it's gratis software, but it's not open source freedom oriented software. And so you could have something that's both. But then when we get into matter, we have this other issue. And that is that the actual material that things are constituted out of, even though the design might be open and you might be able to, make that thing for a trivial amount of money because of the way that the global economy is set up, you might not have access to the raw materials of that thing. And that's the real trick here. And so what I'd like to propose is when we talk about open source objects, we need to talk about free as in dirt, which is to say it's ubiquitous, it's everywhere that there is life. And so it is a kind of like a fundamental aspect that we can try to aspire to achieve. And so let me talk a little more about what I mean by this trifecta here. But before I get there, let's talk about why I care about this stuff. So a little history about me. I started off as a kind of an environmental blogger. I'm a product designer. I teach industrial design at the University of Washington. And before I did that, before I went back to school and got my master's, I was writing for Treehugger about how to be eco-friendly. And that was mostly, things like recycle, whatever. And I got asked to write this book, which basically takes concepts and tries to break them down as to should you use natural fibers? Well, there are pluses and minuses. And it really, looking into these questions, really made me realize that in most cases, there are no hard cut and dried good answers, as long as you are holding some assumptions, like you're going to be in a kind of centrally produced, globalized manufactory. As long as you're going to do that, it's very difficult to make it eco-friendly. It's always a choice. There's always a choice. And so this book writing process really broke my brain and made me less optimistic about the kind of eco-design movement. But when I got my first job teaching at UW, or my first teaching job at UW, I really started thinking about, well, what does that really mean? What would it really mean to be a more environmentally responsible product? And so I started thinking about things that were more like ecologies of parts and replaceable parts. And this was before, this was well before phone blocks. This was right when kind of maybe a little after Arduino and a little after the kind of open hardware, electronic hardware movement was really getting rolling. And so I was trying to think about how could those things work. And I got to have a TED fellowship and speak at TED Global in Oxford about this stuff, about having these kind of recombinatorial aspects of products. But even that, using products that were still made in the global economy with extraction-based mining and all this kind of stuff, it still kind of rang a little bit hollow, because you're just extending the life of products. You're not necessarily allowing for them to be, again, truly open source. You just make them be more remixable, and you still need to have this globalized infrastructure. So here was another concept. This one was an actual functional electronic device that used some non-Arduino open packages, open components, and some Arduino open components, and some 3D printable components, and some sewable components. I mean, it was a whole mix of stuff. So in getting there, I really learned a few lessons, and I think I wanted to start with those lessons in this talk, and then talk a little bit about some suggestions, some seeds that might grow into this future alternative. The first one is this idea is that sustainability is about resilience rather than being about being waste-free or whatever. The end goal is to be resilient, right? It's not necessarily to be sustainable. It's the reason you do it is because you want the resilience. And there are plenty of examples I could give. Hurricane Katrina was a really motivating one for me at the time that I was in grad school. It utterly shut down supply chains within New Orleans, and you could see that there were all these people suffering because they didn't have access to things that they needed in the immediate aftermath of this very, human precipitated but natural disaster. And likewise, we're in a similar one now. I use this image because many of you may not know we have a global plexiglass shortage right now. If you're a restaurateur or somebody and you want to get plexiglass for your sneeze guards, it's crazy expensive. It's very difficult to obtain, and that is, plexiglass is not a hard thing to make. It's just something that we've never made at the levels that we need to make right now. And we won't need it. And we're going to have to make this sort of wartime effort of plexiglass production. And then we're going to have to spin those plants down. So there's a cost of doing that extra effort, whether that's overtime hours for the employees that are trained on the tools, or getting more of the tools themselves converted over to make this sheeting rather than something else. It's a really, again, just like a weird problem and emergent challenge within this unexpected, most of the time, I think when you think of pandemic, you don't think of it's going to screw plexiglass over, right? Like plexiglass is really going to be what gets hit. And so that, I think, was just fascinating for me. Second one, so if we're interested in resilience, then we need to think about what things are resilient. And it turns out there is no good way to make, from my perspective, there is no good way to make mining-based resource extraction resilient, whether that is things like complicating oils into plexiglass, or whether that's getting rare earth metals or whatever that you need to make consumer electronics. Those kinds of material resources will be depleted. And even if we are able, and it's a big if, to go and do asteroid mining or moon mining or any of the various things that Jeff Bezos and Elon Musk really want to do with these space companies, we will still be trapped in the same loop. We may be able to expand our human civilization further, but then it will just be more difficult when we hit that next wall, right? Of the moon ran out of tantalum rather than just the Earth's crust ran out of tantalum. So it's a, you can pass the buck down a couple generations, but there is a way to solve it, and solve it in the way that life has solved it over generations. And that is to derive your raw materials from the soil and from the air, and to do that via an interrelated set of animals and plants that operate in an ecology. And so, just for those of you who have not thought about your food systems very much, here it is. This is some corn in Iowa, and this is what we do generally when we're talking about engaging with the soil system to make products, whether those are food products, or in this case, they could just as likely be PLA plastic for 3D printers made from the starch from this corn. So we plant a monoculture. We have to treat it with incredible care and spray it with tons of pesticides and subsidize it with minerals that we mine somewhere else, because it is super delicate. It's not a resilient system. And so my goal here is to avoid disasters like this one. This was the Gros Michel banana. You all now eat Cavendish bananas. They are, by all accounts, less delicious and, less wonderful than this one. But this one, in the early 1900s, was subject to a fungal disease that wiped out all the plantations for our global system of producing bananas. You can still find them in some tropical places where kind of bespoke producers make them. They can survive for a little while, but there's no way to make giant monocultures of them anymore, because this fungus is totally pandemic and has wiped out any large plantation of these bananas. And the Cavendish is also now being attacked by a fungus, and it is going to have to be replaced. We will have another banana. My kids will not eat Cavendish bananas. They will eat some other banana. Which is wild to think about, right? That's like 2 generations of people have had to give up their bananas because of this kind of monocultural system that we're stuck inside. We also have serious resource depletion because of that. This is a map of the estimated topsoil loss and different kinds of mineral extraction that are happening in the American Midwest, in the watershed of the Mississippi River. And then this is also an overlay of the eutrophication of the deoxygenation that happens in the Persian Gulf, or in the Gulf of Mexico every summertime because of those minerals that get leached out. So the topsoil comes out, it feeds a bunch of algae, the algae blooms, it sucks up all the oxygen as it decays, and all the fish die off. And so that cycle has been going on, since probably the 50s. It's really been accelerating because of planting techniques that we have put in place and watering techniques that we put in place that really accelerated topsoil loss since the 50s. So that's another issue with this. And there are people like Wes Jackson who are working on at the Land Institute, working on doing perennial crops rather than these annual crops. You can see an annual wheat on this side with this tiny, tiny root system that doesn't hold soil in place, and a perennial, I think this is Kernza, intermediate wheatgrass, sort of an improved perennial wheat grass thing that you can see this regrows from a dormant plant every year, so it doesn't die back and get harvested and then the soil is bare all winter. The roots stay, and so it grows. It spends some energy growing roots, but those roots go, you can see, much deeper into the soil, even down, you can see roots all the way down here. And those roots really can extract a lot more water in droughty times, but they also hold the soil in place a lot more aggressively. And so it just makes for a much better soil building kind of crop, even if it's a monoculture. However, there's no reason to stick with monocultures if you really think about how the farm can be aligned. And so this guy, Wendell Berry, really inspired me with, he wrote an essay called Let the Farm Be the Judge about how your engagement with the land that you are on. He's a poet and farmer kind of guy, and he was writing about sheep, but it really spoke to me about, what if we were making consumer products, and what if we were making consumer products using the resources of a place, and what would those resources be, and how would that place decide those for us, because of the kinds of plants we could grow and the kinds of plants we could grow together. So his work is super interesting. So this idea that open source is not enough for making this whole thing possible. Sure, you can share the code, and you can share 3D files for an object, right? If you wanted to make a chair, you could share 3D files for that chair, and you could even share, formulae for the plastic for that chair, and the, the metallurgical spec for the rivets and all that kind of stuff. But you still need to get those resources. In this case, we have coltan is a tantalum ore that gets mined in all over the world, but primarily in Congo, and in and around Congo. It has some of the richest reserves of this mineral. And this tantalum is a very rare mineral in the Earth's crust. It's not rare absolutely in the universe, but it happens to be rare in the Earth's crust because of the way that it alloys with other minerals that are heavier and all this sort of stuff. So in order to get this, you often have resource conflict that can be driven by this, because it's in a place which has had many different layers of destabilization of its local communities and governments, and it has overwhelming demand for this thing that is, the number of these are used in cell phones and video game systems and all these capacitors. They are used in lots of radio frequency devices, or fast response devices. And so if you think about how much consumer electronic demand there is in Congo, it's reasonable, but it's not overwhelming. And so the country can't satisfy all the demand internally. And so a lot of it gets exported. And because it gets exported, there's excessive demand outside. And so there becomes this kind of perverse incentive for maybe a warlord or a corrupt official or someone to look the other way when people's human rights are being trampled on, to do the extraction of this, or to not put in place good environmental protections that would help people to do alternative things that they might want to do, like restorative farming or watershed protection or that sort of thing. That is just because it's not economically, it doesn't make economic sense. It makes more sense to strip mine this area. So when you're thinking about the periodic table, one of the ways to think about it is to think about how are these things formed. And if you see number 73 down there, right, tantalum, that's a beefy molecule. It's got a lot of neutrons. It's heavy. The way that these things form is you start with a star that's hydrogen, and that star fuses things together, and it fuses nuclei, fuses. You get helium, you get lithium, you get barium, you get boron. You work your way up, okay? And each time you fuse nuclei together, some energy is released, okay? Until iron. If you have two iron nuclei and you fuse them together, it actually requires energy to do it, okay? It does not sustain the star. And so once your star gets a core that's made mostly of iron, it starts to cool off because every new fusion event sucks up energy. It doesn't release energy. And that's when you get situations like your star just turns into a white dwarf and it doesn't do anything, or your star, whatever, it just gets smaller and smaller. It becomes this kind of like dead, cold, stony star, red dwarf or whatever, okay? Only in the rare cases when you have a supernova where it explodes, right? It has sort of a supercritical mass and collapses on itself, and that pressure causes it to to jump past the iron barrier and do some of these other fusions that release more energy. And then you release a ton of energy and everything's great. That's when you produce things that are atomic number 27 and above. Okay, but other than that, you're stuck with iron. Okay, and so if you look at some of the minerals that we use, some of them are great, right? You got aluminum, awesome. You got silicon, sweet. You got iron. You got, some chromium or titanium. You've heard of these. But then if you look also, you might notice that like platinum, iridium, gold, silver, those are all much bigger. Or rhodium and palladium are also used a lot in consumer electronics. Even simple things like nickel and copper and zinc, right? Gallium that's used in gallium arsenide photocells, or different kinds of different kinds of transition metals that are, indium that are used. Indium tin is used to make the clear conductors that coat different kinds of displays, right? These minerals are rare because of physics. They're not rare because Earth was a bummer planet. They're rare because there are not very many supernovae in the history of the world relative to other stars. And so we need to be conscious of that. We shouldn't be relying heavily on these things. And if you look at nature doesn't. Nature doesn't use these higher atomic number minerals in any significant concentration in most cases. In fact, if you look up at the top, you can get away with everything up to about, maybe 16 or 17, right? So chlorine, once you start getting into chlorine, you've got your phosphorus, you've got your nitrogen is up there, you've got your potassium is interesting. Potassium is a little heavier, but you got potassium and calcium. Those are like the metals other than iron, which we use for blood, but we use so little of it, right? We use a lot more calcium because we use it in our bones. That calcium, that's the last big one that we really use metal wise. And potassium is the last big one that plants use in a bulky way. And so most of them are these small. If they're using these very low weight minerals because they're super abundant. They're just everywhere. So that's something we need to consider. We need to think about when vegans talk about like eating low on the food chain, makers should think about like making low on the periodic table. If you can make something out of these low atomic weight materials, it's going to be a more, you're going to be able to source the materials more easily in a physics driven sense, not necessarily in a global economy driven sense. So are 3D printers the answer? Well, this thing is great. This is the Prusa, the newest Prusa. It's an awesome open source 3D printer. Prusa printers are amazing. This one is fabulous, but it still requires, these either petroleum-based plastics, or it requires a crop-based plastic that comes from a big industrialized monoculture, right? It is not possible for you easily to make PLA yourself. It's a biopolymer. You could theoretically make it. I have yet to see somebody try. I have yet to see somebody do it successfully. I know that the chemistry that's used by Dow and Cargill and these guys is a very dangerous high volume chemistry. It's not something you could do in your garage. And so that's a thing. There certainly are people like Precious Plastic that want to regrind plastic into filament so that we can reuse it, and that's fine. But this is not a 10,000 year plan. This is a maybe 500 year plan, which is great. Get us those 500 years, but somebody's got to be thinking about an intergenerational strategy for this rather than just how to get my kids' kids to have 3D printers. And then lastly, even if you were able to make the plastic yourself, the computer chip that you're using to run the computer controlled manufacturing or the motors, the CNC core of that 3D printer or whatever other robotic fabrication device you're using requires this extremely energy intensive and material intensive and complexity intensive chip fab plant in order to make. It's just not, with the way that we make consumer electronics today, it's not possible for you to make even this relatively basic 3D printer control software or hardware, right? So even this thing, not possible for you to do. So what is the challenge? The challenge for us is to reimagine manufacturing so that rather than, at worst, mining something and using child labor and whatever and having everything be patented, what if instead we were to reimagine it so that every object, when it was made, reinforced a healthy ecology where humans could cohabitate in that ecology? So it basically, imagine making a phone that builds a forest. Like, the phone requires a healthy forest. It's not that it doesn't damage a forest. It's not that it allowed for, a replanting of a mine site, which is what the best objects do now, right? They say, oh, we're going to buy some kind of allowance for our damage, and they're going to reinvest to cover the damage they've done. No, this would be something where the act of making it reinforces a positive loop that exists. So how could we possibly do that? Well, this is what we're up against. This is the current thing. You've got like people totally isolated from any sort of engagement with this natural space. This is a grape vineyard in, I believe this one is actually in Portugal. But so this is a grape vineyard. People are harvesting these grapes. It's highly automated. This is as mass produced as you can get. And this, people do interact with these grapes. People walk through them, but nobody hangs out in this grape vineyard. It's not a place to party. It is a strictly agricultural space. And part of the reason for that is it's a monoculture, so that you need to maintain it with pesticides and herbicides, and so that makes it toxic for everything else other than the grapes, which is, what are you going to do? This, on the other hand, is my buddy Joel's farm in West Virginia, and this is much more of a sort of cohabitative space. He has horses that live next door that he borrows to plow it. He lives on the farm. He plays with his kids on the farm. The farm exists as a place for him and his family to live, as well as the crops, the materials to be extracted from this collection of plants. Now, this is not a perfect solution by any means. It's still tillage based. They still they mostly sell fruits and vegetables, so they get relatively low returns for the stuff that they're selling, because there's just not a lot that they can compete with. There's not a lot of value add they can do. So this is part of the way on the path, but it's not the whole way. So I have 6 ideas that I think are valuable to consider when you're developing this new, when we hopefully are developing this new strategy together. And I've got some examples of people following one or more of the guidelines as we go along. Unfortunately, there really are not very many people trying to make an alternative manufactory or technium that is this comprehensive. And so that's why I'm talking to you all today. So I should preface this. I run a lab in Seattle. It's my basement, but this is how we do things. So that's the Humble Factory. So some of this stuff is mine. Where there are other people's stuff, I've called out those people and given you links to follow. It's my house. This is about 6 years ago. You can see we started with a pretty normal suburban lot, and just sheet mulched everything, and then planted it out with, I don't know, we've probably got around 300 or 400 different species of stuff. Fiber plants, dye plants, some medicinal things, a lot of edible stuff, structure plants for physical materials, and really trying to push this idea of guilds and polycultures, and we'll talk about that in later on. So here are the 6 points. Number 1, no mining. Number 2, preserve complexity. Number 3, scaffold growth. Number 4, breed for NetShaped parts. I'll explain what I mean by that. Number 5, democratize the tools you're using, so make them cheap and available and open source ideally, and makeable by someone if they are open source. And then lastly, design polyculture. So really think in this polycultural rather than a monocultural frame. So no mining. What I mean by that is literally no mining. Do not dig up the dirt. If you need to make a raw material like an organic molecule, don't use petroleum. Use a feedstock from something else. You may or may not be aware that Thomas Edison was obsessed with this later in his life. He was really committedly breeding goldenrod, soldago species of goldenrod and hybrids of goldenrod. This is one of his, normally these are a plant that's like 4 feet tall, and this one is, you can see, pretty extreme. And so this plant has a natural latex and is native to the American Midwest. So it grows in a lot of different climates. I have it in my garden, and you can make a rubber from it, and you can make a cross-linked, a sulfur cross-linked rubber like the vulcanized rubber in your car tires from it. And this is actually a car that so this is a Model T that Edison had outfitted with a set of these soldago rubber tires. Now this rubber is not as good as the rubber on your tires, okay? But that is not because it couldn't be. That is because the rubber on your tires has had 150 years of, or let's say 100 years of research and development around it, and this has not. So this is just this. The reason that you don't know about this is that no one uses this for anything. I'm not saying we could replace Goodyear with this. I'm saying that there must be some positive path forward that includes this kind of member of a guild system. Similarly, and even more weirdly, there are a number of plants in the world that are hyperaccumulators. So see, these are plants that do what's called phytoaccumulation, where they accumulate minerals in their tissues. Most of them are early pioneer species that go into like a burnt out place or a place where there was a landslide or some kind of like volcanic eruption where there was a lot of a mineral present, like arsenic, that kills everything, and they accumulate that arsenic so that other plants can come after them, right? So they extract the arsenic from the soil and then die in their tissues, and they accumulate in the very top layer of the soil, but the lower soil is better. There are some plants like this one, which I don't actually know the species. It's in New Caledonia, but this tree has, up to like 8% nickel in its sap. It's just an absurd amount of nickel, to the point where you can literally make money by tapping this tree like a maple tree. It's not a common tree, unfortunately. It is there are not very many crazy nickel-rich deposits in the rainforest in New Caledonia, and so because of that, this is a relatively rare species of tree. And so I'm not saying go out and cut this tree and get the sap and make yourself a business. That's not what I'm saying. What I'm saying is there are many, many other kinds of plants like this, and if you need to make metal for your project, this would be a very interesting way to do it. You still have to abide by that rule. Nickel is heavier than iron, right? So you still don't want to use like bulk nickel to make your thing. But if you're going to make a nickel coating on something, this tree would easily provide for enough, and you remediate a mine site at the same time. So this tree can productively grow on mine tailings that are crazy toxic with nickel, but are too expensive to clean up any other way. So it's a really interesting win-win. If you were to like reforest a mine in Denver or somewhere that was an ex-nickel mine that had played out as far as our mining extraction techniques are concerned, but because this tree is so efficient, it would be able to extract that last little bit. Unfortunately, this one's a tropical tree, so it can't grow in Denver. But there are hyperaccumulators for nickel that are temperate, that would be able to do this kind of thing in that context. Second seed, preserve complexity. So if you are going to harvest a thing, don't make it simpler just because that makes it easier for you to think about. Try to think about what kinds of valuable shapes or chemical structure or aspects that resource has before you turn it into something. And so one example of that is Whole Trees is a company that is very difficult to describe. They're sort of they're a software platform and business to business operator. And so what they do is they know a bunch of foresters in the American Midwest. And they have gone into their forests, and these are managed forests. So in most cases, when you're managing a forest, you kind of know which trees you're going to cut when and what value they would have. These guys have just taken it to an insane next level where they have 3D scanned many of the trees in these forests, and they have those scans in a database. And so when someone wants to design something like this, this bandstand, they can go into their database and they can say, I need a tree with 4 branches that branch out at angles sort of like this. And then they also have technologies that allow them to assess the standing living tree so that they can include the structural integrity of that tree in finite element analysis models. So they can actually like assess the tree to see how much weight it could support given, it dried out and whatever. And then they have warehouses where they dry the tree. So they have the whole thing. So if you want to go and like pick a tree out to make a part of your house, you go in their database, you shop for the tree, it gets integrated into your build plan. It can be to code because you can get an engineer to sign off on it because the tree has actually had like modeling done to show they've shown we can use this. It will it will support this load, etc. So yeah, wholetrees.com. Go check it. It's just completely amazing. And so while that is cool, it's incredibly it's out of reach for most people. Most people are not designing a house. You might want to build a bike, and you might have pruned some bushes in your yard, and you might have 100 different bush prunings, and you'd like to categorize them by shape. And that would be a lot of work for you. But because of things like the Coral TPU and other kinds of artificial intelligence accelerators that are being sold. So this is this little guy here in the middle is an offline, it's like a graphics card for AIs. So it allows you to run TensorFlow without a super beefy computer. So this thing uses a Raspberry Pi and this sort of graphics card, this accelerator. This one was built by these interns at Google, and it categorizes marshmallows. It does marshmallow or not, and it tips them into one bowl or the other. So you can pour in some marshmallows and then, go away on your lunch break, and then you get a marshmallow snack when you come back. And you can build this. It is open source. It is buildable by you. I would not advise you to build the marshmallow thing because it's dumb. Build something cool. Build a tree crotch sorter or a bean sorter or a general purpose sorter that you just teach it with a couple of photos so that then it knows, oh, these are the things that they want to do. Cool. These kinds of things, these kinds of teachable sorting devices will have so much potential to revolutionize the reuse of shape in the harvested environment. And no one is doing that stuff. You should grow on scaffolds. You should make scaffolds and grow on them. So this is grown by Jen Keen is amazing. It's a way of making shoes using bacterial cellulose. Bacterial cellulose has been done in the past. The problem with it is it's pretty variable, and the real secret sauce that she did was she added this added a thread that's a CNC sort of woven thread structure. And so what happens is you weave this thread on this in this complicated tub over these little pegs, and then you grow some basically kombucha. She's using a bacterial culture, but it's more or less kombucha. You grow this kombucha through it, and so all of this nanocellulose grows through these fibers. Once you dry that out, you end up with a really, really rigid but also known shape object, right? Because it had this scaffold that it grew around. You could do this with lots of different things. You don't have to do it flat. You could do it in a shape. You could, there are so many things that you could extend from this initial work, but it's great work, and she's really doing incredible stuff. She's working for Adidas now. This is a pavilion project. This thing is maybe 15 feet tall, and this is a pavilion project by Zaha Hadid Architects, but in collaboration with the Block Research Group, which actually sort of develop this work. And what they're doing is they have a CNC knitted scaffold that is then stretched under tension to put it into a taut configuration, and then you spray it with some resins and some concrete, and that stiffens it, and then you can take away the framework. So you can see this guy is spraying with some resin there, and you can see some of the formwork. It's very minimal formwork, so the formwork itself is actually very cheap to install. And this whole the entire knit thing was 180 kilograms and was carried in 2 suitcases from Switzerland, where the research group is, to Mexico. So it's a very portable, whereas building this normally would take probably hundreds of pounds of lumber that was carefully fitted to this shape. So this is a really incredible achievement. And it's CNC. That's the other thing that's super cool, is this computer controlled knitting, man, is great. Breed for NetShaped Parts. Why are we not doing this? We have people breeding for really interesting foods. And so Dan Barber, in collaboration with Michael Mazurek, who's this breeder at Cornell, have been developing these foods that are like specific to the high-end restaurant industry. So you've got the 898 squash is a teeny tiny little single serving butternut squash, literally designed to be a single serving butternut for roasting for restaurants. So it roasts faster. It has nice flavor profile too, but it's designed to be used in that kind of fast roasting way. Or you have the tetra squash, which was designed so that every stage of the squash can be eaten. So you can eat the immature fruits. It's a delicata squash. So it, like, when it's mature, it tastes like a delicata. When it's immature, it tastes kind of like a weird cucumber that you can use in salads and stuff. You can also eat the stems. The stems are nice and sweet and are soft and non-stringy. They've been bred for non-stringiness. And then you can also eat it for its flowers. The flowers have been bred for edibility as well. So it's got this 4 different kinds of edible thing at different stages in the life cycle, so that the farmer can make more money off of planting this single crop if they're working with a restaurant. So Row 7 Seeds is actually selling this stuff. You can grow it yourself if you're interested. Why aren't there people breeding for objects? These kinds of objects are already available in nature. And just imagine what would happen if we took these just a little bit further. Up top, you've got Job's Tears, which is a tropical grain crop, but it grows as a bead. It is a grain that each grain, without extra work, has a hole through it when you pick it, and has a very shiny seed coat. And it's pretty durable. So these are literally as if they were bred to be a bead, and you could, if you were interested and you were trained as a seed breeder or plant breeder, you could breed these into, different sizes, shapes, sort of conformations. You could do things with these, right? You could mess with different colors, all that kind of stuff. Nobody's doing that because there's just not enough demand for seed beads. Similarly, when I think about things like deer antlers, which grow back, this is a raw material that grows back every year. It's a bone that doesn't hurt the deer, that grows back every year. Think of it like a cow that you milk, right? Like, imagine if that bone grew in the shape of the housing for a game controller, or it grew in the shape of the spar for an ATV, like the Y suspension neck for ATV, right? Why are we making that thing out of stamped steel? Which, fine, I understand why we're making it out of stamped steel now, because nobody's bred the deer to be like ATV deer or whatever. Like, imagine if we had just 10 generations of breeding. Imagine, think about how much a pig, the different pigs that we eat. When you see a pig in a video about pigs and about agricultural hogs versus wild boars that you see at the zoo, the difference between those, the physical differences, imagine the physical differences we could make possible in animals like these, and the structural objects we could get from them. And when we think about those kinds of things, we need to think about the tools we're using to do those. Now, there's plenty of actual fabrication tools that we use, but I'm thinking about other kinds of tools that have not yet been democratized. And I know that Cory Doctorow, who's speaking at the conference, has done some work thinking about what are ways that the open sourcing of fabrication tools, not necessarily 3D printers, but he's done a lot of stuff, especially in Walkaway. They do a lot of bioreactor stuff. I mean, he doesn't talk about it very much of how would people actually do it, but I think it's really important to read books like these and then really think about, well, what would I do with a bioreactor at my house, right? And so there are people that are working on open source bioreactors. A bioreactor, by the way, is sort of like a raised bed garden for a yeast, or you could make beer with it, but you can also make if you needed an enzyme that you genetically modified a yeast to produce, and then you need to grow a bunch of that yeast so that you accumulate a bunch of the enzyme, or if you had a protein that was maybe was like a fluorescent protein or something like that, and you inserted it with CRISPR into some yeast or bacterium, and then you need to grow a bunch of that yeast or bacterium. That's what this thing does. It's an appliance that amplifies the presence of a culture. And so it's super important for so many things in microbiology, but it is especially important for using biotech to produce bulk materials, because you need to make a lot of the thing. And so this open bioeconomy, these open bioeconomy guys are awesome, and they're super successful and Shuttleworth funded and everything, but they're doing really cool work, and they're doing a great job publishing their stuff. And so definitely check them out. I would also say we don't necessarily need the very high-end computerized stuff. In a lot of cases, we need people doing selection for, similarly, like the plant breeding stuff, for these kind of molecular knives. So if you are someone who makes your own miso or your own kind of koji altered proteins, whether those are meats or pickles, you know that koji varies. The different kinds of koji, the substrate it's grown on, whatever, this stuff, it matters how it's made. And I can imagine other kinds of koji, or other kinds of, maybe not koji, maybe these are other kinds of aspergillus that are not for eating, but they are for treating wood to make it darkened or to make it flexible or to make it whatever. And you could grow a mushroom that was dead and then soak the wood in that thing exactly the way that you're doing. You know, this koji is not alive. This particular stuff comes freeze dried. It's not, it's already been grown out and then sort of deactivated. And so the mold is not going to grow anymore. But and imagine if you could take